Hi guys, this is going to be part one of a short two-part review for the quiz that's coming up on work, power, machines, mechanical advantage, and efficiency. So here we go. This was the warm-up slide that we went over. Let's just go over those problems again. This one was your famous Biff, Uncle Biff. He wants you to invest in a machine. He says that machine will output a force of 1,000 newtons through a distance of 1 meter, and all you have to do is exert 50 newtons through 2 meters. And the question is that a machine that would satisfy the conservation of energy? So here, whoops, okay, I'm going to have to start, I'm still learning here. Okay, so conservation of energy says that the work that's going to come out of your machine almost always is going to be less, but at least theoretically will never be more than the work that comes out in, the work that you put in. Okay, so let's figure the work that comes out is force. The force that comes out times the distance through which it works, and it's got to be less than or equal to the product of your input force times the distance through which you exert that force. Well, I think we can see a problem here. There's going to be 1,000 newtons coming out, and that's going to be done through 1 meter. And is that less than or equal to 50 newtons times 2.5 meters? And the answer is no. Okay, so this is 1,000 joules of work that will come out, and your uncle claims all you need to do is put in 125 joules. So let me find red here. Okay, no, that completely violates conservation of energy. Okay, the next question. A machine has an actual mechanical advantage of 3. What would be the output force if you provide an input force of 10 newtons? Well, AMA is the actual force out divided by the actual force you put in. So this is 3. You're going to be putting in 10. Okay, I'll just do a little X there for the output force, and you can see hopefully that X, which I should really say that is your F out, is going to be 10 times 3 or 30 newtons. Question number 3. Suppose the machine in the previous question had a TMA of 10. What is the efficiency of this machine? Okay, efficiency, which I just use this weird E, is, well, really what it is the work that comes out of your machine divided by the work that you put in. But as I showed in class, and as you'll have available on the quiz, you can get that ratio by taking the machine's actual mechanical advantage, which is the actual mechanical advantage, and then basically dividing it by what theory tells you it should be, and that of course is the theoretical mechanical advantage. So here we have a TMA of 10 that goes on the bottom. The actual mechanical advantage is 3, so that is 0.3. That is a totally acceptable answer, but I might give it to you, or you can also write it in terms of percentage. That's 30%. So only 30% of the work you do comes out as useful work. However, it still may mean that you can do something you couldn't do without the machine, so it still might be worth doing. Next question. What is your power output if you do 1,000 joules of work in 10 seconds? Power is the rate at which you do work, or an object does work. So that basically is the work done divided by the time it took to do it. Here we have 1,000 joules of work being accomplished. It takes 10 seconds. Do the math. That is 100 joules of work per second. And in honor of James Watt, who worked with steam engines to improve them, we call that 100 watts. Okay, so capital W is for watts. Moving on. Okay, so now we're ready. In this video, we'll talk about work and power. In the next video, we'll talk about machines. Okay, so you should definitely know what work is. Work is a force acting through a distance. And let's hear some questions. Biff pushes on an exercise sled with 1,000 newtons of force. The sled travels 8 meters. How much work has Biff done? Well, work is force times distance. We have 1,000 newtons of force acting through a distance of 8 meters, and we get 8. Whoops, something's going on with my pen. I'm still learning. 8,000 Newton meters. Okay, we're not going to usually see Newton meters. You can write it. It's completely correct. However, that has been a Newton meter is called a joule in honor of James Prescott Joule, who did some foundational work in energy. So that is 8,000 joules. That's a pretty easy question because it's just plug and chug. Okay. Biff pushes on a wall with 1,000 newtons of force. Let's see, where is my mouse? There it is. The wall doesn't move. How much work has Biff done on the wall? Well, work is force times distance. Here we have force for sure, but we have no distance, so that is 0 and a unit, and so that is going to be 0 joules of work. So you may be exerting a force, but unless you're pushing that force through a distance or pulling, then we say you're doing no work. So we've talked about the next question, which is, okay, so why do you get tired then? And that has to do with the way your muscles work. Whoa, what is up with that? The way your muscles work versus a table. Okay, in the muscles you have these striated muscle fibers and all that. And okay, I am not a physiologist, but this one will contract and release, and as that one's releasing, this one contracts and releases, and then same thing goes on here, contracts and release, and then this one goes back, and there's this constant kind of tag team of muscle fibers contracting all the time. And so you are doing basically work internally, and basically you're getting warm. And your muscles will get tired doing that. But what's happening is you are not doing any of that work on the weight. You're not making it get any higher or go any faster. Where the table, where are you? There you are. The table, all it does is just flexes. The bonds are compressed. They don't fire, they relax, fire, then relax. So the table just sits there with the bonds compressed, and it can do it for a long, long time. Thousands and thousands of years if the table is, unless the table's destroyed. Okay, moving on. Here's another topic that is involved in work, which is we have a skating waiter. And he's moving, he's exerting a force. He is exerting a force upwards. It's a normal force. It is going to be, there's the mass, so it's going to be actually, there it is, 20 newtons. And even though he's coming right toward us, we'll just say, here he is, carrying his tray. He's exerting a force of 20 newtons. He's moving through, and actually the object is moving through a distance of 20 meters. And so don't fall into the trap of saying work equals 20 newtons. This is a mistake that I'm doing here. Don't do this. You say, well, that's 400 joules. No. Okay, why not? Why is he not doing any work? Well, let's draw him again. And And the reason is because his force, okay, his hand has to come under here if he's going to be exerting this force. This is the force, and it is a real force. It is 20 newtons, but the motion is this way, and the force is perpendicular. So when these are perpendicular, there is no work. At least some of the force has to be in the direction of the motion. Here, it's completely perpendicular, so no work. Okay, well, here's a good question for the quiz. We have a young lady who is exerting a force that way, horribly drawn, a tension pulling force, and the motion is this way. So this is the D. So what we have is we have a force this way. Okay, I lose my cursor. And then the motion is this way. Okay, well, you can see that the force is not in the direction of motion, really, but it's also not completely perpendicular. So we're going to say that some of this force F, so this is the part of the force that's parallel, that you get credit for. Okay, so there is some work being done. It is not 40, so she's pulling, it is not 20 joules of work. So that would be if all of the force was in the direction of motion. And it's also not no work because some of her force is in the direction of motion. And of course, the most you could have is 20, even if it was all in the direction of motion. So that can't be C. So the correct answer is D. Less than 20 joules, but not 0. Okay, and I think I've already just said, why does the woman do less than 20 joules of work? Because some of the force, but not all of it, is in the direction of motion. Okay, power equals the rate at which we do work. So, Biff does 1,000 joules of work in 10 seconds. What is Biff's power output? Okay, so power is the rate at which we do work. Biff does 1,000 joules of work, and he does it in 10 seconds. This is basically the warm-up, so 100 watts. Okay, this is pretty easy because you just plug in the work goes in the top, the time goes in the bottom, and you just do it. This is what we call in physics plug and chug. You plug the numbers in, and you chug through the calculation. Here is another kind of question you might see on the quiz that is a little bit trickier. So you might get one easy one and you might get one harder one. Okay, so here, Buffy pushes an exercise sled through some distance. Okay, first with a force of 150 newtons. So that is the force. And we see that she does it through 10 meters. So that is the distance. And we see that her power output is 300 watts. And the question is how long? So it's asking for time. So let's just start playing around with the power relationship. Power is the rate at which we do work. Work divided by time. We can rearrange that algebraically. Just multiply both sides by time and we get T. Okay, we're also going to basically divide both sides by P. So we're going to get the time it took her is going to be the amount of work she did divided by the power, which is the rate at which she does work. It's a little bit like if somebody went 100 miles and they were going 10 miles an hour, how long did it take them? I mean, that's a different, it's not exactly the same, but it's the same kind of idea. We have a quantity of something, and below it is divided the rate at which that quantity is being accomplished or reached. Anyway, so here we have the amount of work she did is not given in the problem. There it is. Okay, so the amount of work is her force times the distance of 10 meters divided by the rate, 300 watts. Okay, so 150 times 10 is 150. sorry, 1500. 1500 divided by 300 is, seems like that's going to be 5, right? Yes, 5 seconds. So it took her 5 seconds to push that sled. Okay, we're going to wrap up. This is the end of video 1.